Okay. Hey guys, Alan here, continuing from where I just left off. So number 20, let T be a triangle in a coordinate plane with vertices 0, 0, 4, 0, and 0, 3. Considering the following five isometries, rigid transformations of the plane: rotation of 90 degrees, 180 degrees, and 270 degrees counterclockwise around the origin, refraction across the x-axis, and refraction across the y-axis. How many of the 125 sequences of three of these uh, three of these transformations, not necessarily distinct, will return T to its original position? For example, a 180-degree rotation followed by a reflection across the x-axis followed by a reflection across the y-axis will return T to its original position, but a 90-degree rotation followed by a reflection across the x-axis followed by another reflection across the x-axis will not return T to its original position. Well, this one, let's think about what's going on. So we have a triangle. We start with a triangle, uh, 3, 4, 5 triangle, in fact, but probably doesn't matter. And we are reflecting this triangle either across the x-axis. So here we get the x-axis. We reflect it across y-axis, or even reflect it across the axis. Or we can keep rotating this diagram. Well, what happens if we reflect the diagram across the x-axis? Well, we just flipped it. But it's actually different from rotating by 90 degrees. If you just rotate the red triangle by 90 degrees, we actually, well, counterclockwise, we actually get a totally different, well, I mean, not a different triangle, but it's a triangle that is a different, like, differently, like, the orientation is different. So we want three transformations that will result in the original triangle. And what we notice is that if there is going to be a reflection, then there needs to be two reflections to change the orientation back to its normal. Either a combination of two reflections across the x-axis, or the two, well, there's a or two reflections across the y-axis, or x reflection across the x combined with the reflection of y. And so what we notice is that in order for the T to return to its original position, the orientation must be the same. Orientation must be the same. And in order for the orientation to be the same, that the number of reflections must be even. And so there needs to be either two y reflections or two x reflections, or x reflection followed by, or reflection, x reflection plus y reflection. It doesn't matter which order we're doing them in. But we cannot just do two y reflection, because we only have three transformations total. And if we do two Y reflections, essentially these two Y reflections will negate each other. And if we do a rotation, we'll never get this triangle back to its original position. So we can safely rule out the first two cases. Oh, by the way, also there could be no reflections. Okay. So if we do an X reflection and a Y reflection, what we just did is essentially we reflect it across the origin or a 180 rotation. So in order to return the diagram back to the normal, we need to also add in a 180-degree rotation. So the number of ways to do this case is 3 factorial equals to 6. Let's say we do no reflections. Essentially, what we need to do is we do a bunch of rotations. We want to make the diagram back to its normal, so the total number of degrees of rotation must be a product of 360 degrees. And the maximum number of degrees we can rotate by is 3 times 270, which is 810, my maximum rotation. And since we want the total number of rotations a product of 360 degrees, it must be either 360 degrees or total must be either 360 degrees or 720 degrees. And to do 360 degrees, we could do 90, 90, 180. That's the only way that's possible, which gives us 3 factorial divided by 2 factorial, which is 3 ways. If we do the 270, well, we must have a 360 degree. No, 270. We need some 270s. Then if we do a 270, we get 450. So we need a 180, 270, 270. And this has 3 factorial divided by 2 factorial, which is 3 permutations. And these are all the ways that's possible. And therefore, the number of ways to do, number of different like a sequence of 3 transformations that we have is 6 plus 3 plus 3, which is equal to 12. And therefore, the answer is A. Okay, number 15. How many positive integers n are there such that n is a multiple of 5 and the least common multiple of 5 factorial and n is equal to 5 times the greatest common divisor of 10 factorial and n? Okay, so let's write it in mathematical terms. So the LCM of 5 factorial and n is equal to 5 times the GCD of 10 factorial and n. Well, unfortunately, we cannot use the Euclid's algorithm here because we don't know what n is. So the only way to relate, and we cannot just use the formula that the product is equal to GCF times the LCM, because we don't know what so I mean, if you write this as, no, sorry, the left side as 5 factorial times n divided by GCF of 5 factorial and n, we don't really know what is the GCF. So it doesn't help us anyway. Well, what we could do here instead is think about factors, right? Prime factorizations of n. Okay? And we notice that if n has a factor other than, well, it has a prime factor, I should say. Yeah, it has a prime factor greater than 10. Let's say, well, prime factor p. Let's say p is equal to 11, for example. This is not possible because if, let's say, n has a factor of 11, then the GCF must, sorry, the LCM of 5 factorial and n must have a factor of p. And p must divide the the LCM of 5 factorial and n. But the GCF of 10 factorial and n does not have a factor of p when p is greater than 10. And that means that 5 factorial, no, 5 times 10 factorial divided, 5 times the GCF of 10 factorial and n cannot have a factor of p. And so there's a contradiction. And therefore, n cannot have a factor of p, prime factor of p greater than 10. And so now we can write n as 2 to the 8th power times 3 to the b's power times 5 to the c's power times 7 to the d's power. And let's prime factorize 5 factorial. So 5 factorial is equal to 1 times 2 times 3 times 4 times 5. Let's count the number of 2's right there. So there's 1 2 in the 2, 2 2's in the 4, so we get 2 cubed. Let's count number of 3's. Clearly see there's only 1 3, so 3 to the first power. Number 5's, there's only 1 5. Now let's count. Let's do the prime factorization of 10 factorial. 1 2 3 4 5 6 7 8 9. Let's count the number of 2's. So 1 2, we have 2 2's in the 4, 1 2 in the 6, 3 2's in the 3 2's in the 8. So the total number of 2's is 7, 2 to the 7th power. Let's count the number of 3's. 1 2 in the 1 3 in the 3, 1 3 in the 6, and 2 3's in the 9. So therefore we get 3 to the 4th power. Oh, whoops, I also have the 10. I left out the 10. Yeah, it's 10 factorial, right? Yeah, it's 10 factorial. So the number of 2's should be increased by 1. So this is 2 to the 8th power instead of 2 to the 7th power. So this is 2 to the 8th power. The number of 3's does not change yet because 10 does not have factor 3. And now let's count the factors of 5. So there's a 5 in 5 and there's a 5 in the 10. So this is equal to 5 to the 2nd power. And let's count the number of 7's. There's only 1 7, which is from the 7. 7 to the 1st power. And therefore, let's rewrite what we know. So we have the LCM of 5 factorial and n. So 2 cubed times 3 to the 1st power times 5 to the 1st power and 2 to the 8th power, 3 to the b power, 5 times c power, 7 to the d's power is equal to 5 times the GCF 10 factorial, so 2 to the 8th power, 3 to the 4th power, 5 squared, 7 to the 1st power, and 2 to the 8th power, 3 to the b power, 5 to the c power, 7 to the d power. So to find the LCM, we take the maximum, the larger exponent. So the max of 3 and A must be equal to the minimum of 8 and A. Well, how is that possible? Well, if A is equal to 1, 2, 0, 1, 2, or 3, that's not, well, 0, 1, or 2, then the minimum of A and A is less than or equal to less than 3, and the maximum is greater or equal to 3. Right? So we know that the maximum, well, we know this, this is the maximum of 3 and A is at least 3, and the minimum of A and A is at least 8. It's at most 8. So therefore, this is between and 8, and therefore, uh, this this means that A must be at most 8, because if A is 8, if A is greater than 9, then uh, the maximum of 3 and 8 is greater than 8, which contradicts with this. And by the same reason, A must be at least 3, because if A is less than 3, then the minimum of A and 8, 8 and A is less than 3. And next, let's count the factors of 5. Factors of 3. So we have a maximum of 1 and B is equal to the minimum of 4 and B. And we know that the minimum of 4 and B, the maximum of 4 and B, this is the maximum of 1 and, the maximum of 1 and B. Uh, we know that the maximum of, we know the, here, okay, let's think. So if 1, the maximum of 1 and B is equal to the minimum of, yeah, okay. So since we have the maximum of 1 and B, we know that the maximum of 1 and B has to be greater or equal to 1. Okay? And the minimum of uh, the minimum of 4 and B, since 4 is one of the numbers, the minimum of 4 and B doesn't matter. It has to be less than or equal to 4. And that means that what this entire thing in the middle is between 1 to 4. And that actually caps B, because if B is greater than 4, then that's not possible. So therefore, B has to be between 1 and 4. And the third one, okay, let me write it in red. So B is between 1 and 4, inclusive. And next, let's see the factors of 5. So left-hand side, we have the maximum of 1 and C. The right-hand side is 1 plus the minimum of 2 and C. And we know that here, the maximum of 1 and C is at least 1. And the minimum of 2 and C is at most, the minimum of 2 and C is at most 2. So therefore, 1 plus the minimum of 2 and C has to be at most 3. Okay. So therefore, C can be between. So therefore, here, because this is bounded between 1 and 3, C must be either 1, 2, or 3. But because we have this here, actually, we need to also check if A is 3 actually works. Right? So the first one, actually, yeah, let's check if A is 3 works. If A is 3, then the maximum is 3. Maximum of 3 and 3 is 3. Maximum of 8 and 3 is 3, so that works. Well, 4 also works because maximum is 4, minimum is 4. 5 works because maximum of 3 and 5 is 5. Minimum of 8 and 5 is 5. 6 also works. 7 also works. 8 also works. So let's check the second one. If B is 1, then the maximum is 1. Minimum is 1, so that works. If B is 2, maximum is 2, minimum is 2, so that also works. If C is 2, if B is 2, if B is 3, then the maximum is 3, minimum is 3, so that works. If B is 4, maximum is 4, and the minimum is 4, so that works. Now let's check if the C is 1, maximum is 1, minimum 1 plus the minimum is 2. So C equals to 1 doesn't work. Doesn't work. How about C is 2? Maximum is 2. 1 plus 2 times 1 plus 2, 1 plus the minimum, which is 1 plus 2 is 3. So therefore, C equals to 2 doesn't work. C is 3. Maximum is 3. 1 plus minimum, so 1 plus 2, which is 3. So actually, C can be only equal to 3 here. Okay. So C can only be equal to 3. This is very peculiar. And the last one, we have maximum of 0. Okay, so this first one is 0. 0 and D is equal to the minimum of 1 and D. And we know that the maximum is at least, maximum 0 and D is at least 0. And the minimum is of 1 and D is at most 1. So therefore, this is bounded between 0 and 1. And this gives D must be between 0 and 1. And let's check if 0 works. If D is 0, maximum is 0, minimum is 0, so that works. D is 1, maximum is 1, minimum is 1, so that also works. And what do we need to find? Is we want to find how many of these n's are here. Well, n can be generated from A, B, C, and D. The number of values of A that works is from 3 to 8, so that's 6 values. The number of B's that work, there are 4 values. Number of C's that work, there's 1 value. Number of D that works is there are 2 values. So number of solutions there are 6 times 4 times 1 times 2, which is equal to 48. And therefore, the answer is D. Number 22. Let the sequence of AN and sequence BN be the sequences of real numbers, such that 2 plus 1, quantity of 2 plus I to the nth power is equal to AN plus BNI. For all integers n greater equals 0, where I is equal to the square root of negative 1. What is the summation of n equals to 0 to infinity of AN times bn divided by 7 to the nth power. Well, the one thing I noticed is that if we apply r cis theta here, this looks very nasty. We need to multiply these two together. We need to multiply an and bn together. But that is essentially cosine theta times sine theta, which corresponds to that is the imaginary part of r cis theta squared. And this should give us a hint that we should probably think about this quantity square. So if we square the first equation, we get 2 plus I times n squared, which is equal to 4 plus 4i minus 1 squared, which is 3 plus 4i squared. And that's equal to an plus bn I squared, which is equal to an squared minus bn squared plus 2ab, no, an bn I. And therefore, in order to get this an bn, we can just consider the imaginary part, right? And therefore, an times bn is equal to 1/2 times the imaginary part of 2 plus I to the nth power. Sorry, no, it's not 2 plus I to the nth power. It's 3 plus 4I to the nth power. Right, 3 plus 4I to the nth power. And therefore, the summation of an bn to the 7 to the nth power, where n it goes from 0 to infinity, is equal to summation of 1/2 of the imaginary part of 3 plus 4i to the nth power divided by 7 to the nth power with the same bound. But adding a bunch of imaginary parts is the same as adding all the complex number first and then take the imaginary part. And therefore, this is equal to 1/2 times the imaginary part of the summation of 3 plus 4i to the nth power divided by 7 to the nth power, where n goes from 0 to infinity. And this is equal to 1/2 times the imaginary part of 1 divided by 1 minus 3 plus 4i divided by 7. That's equal to 1/2 times the imaginary part of 1 divided by 4 minus 4i over 7. And this is equal to 1/2 times the imaginary part of 7 divided by 4 minus 4i. So that's equal to 1/2 times 7/4 times the imaginary part, or 1 divided by 1 minus 1i. And this is equal to 7 over 8 times the imaginary part of 1 plus I divided by 1 minus I times 1 plus I. And that's equal to 7/8 times the imaginary part of 1 plus I over 2. So imaginary part is 1/2. Therefore, the answer is 7/8 times 1/2, which equals 7/16. Therefore, the answer is B, 7/16. Okay. Number 23. Jason rolls 3 fair standard 6-sided dice. Then he looks at the rows and chooses the subset of the dice, possibly empty, possibly all 3 dice, to reroll. After rerolling, he wins if and only if the sum of the 3 numbers face up on the 3 dice is exactly 7. Jason always played the max to optimize his chances of winning. What is the probability that he chooses to reroll exactly 2 of the 3 dice? This is a type of question that has been popping up quite often recently on the AMC and the Amy. This is a strategic game problem. And when I think about these problems, I always think about what is the basic strategy I can do. And the basic strategy is just rolling all 3 dice. We want to get 7. So what's the probability of 3 dice getting 7? First thing is consider what's the probability of 3 dice and we get 7. Actually, sum of 3. Consider probability of sum of 3 dice equals 7. So we can list out all the ways to get 7. So 1, 1, 1, 5, 1, 2, 4, 1, 3, 3. And we don't need to list out 1, 4, 2 because we can just do permutations of each of them. And there are 3 ways to get 1, 1, 5. There are 3 factorial ways, so 6 ways to get 1, 2, 4. There are 3 ways to get 1, 1, 3. 1, 3, 3, sorry. And then we get 2, 2, 3 can also get a 7. This gives us 3 ways. So at worst, we can just roll all 3 dice. And what's the probability of getting 7? That's 15 over 216, which is 6 cubed. And that means that at worst, the worst case we can do is roll all 3 dice and get a 5/72 chance of getting a 7. But we can probably get better than that. For example, we can choose to keep 2 dice, and obviously we got the 2 dice that we're keeping must have the sum of less than 7. So if you keep 2 dice, what happened is that we need to get, let's say, the sum of these 2 is S. Then what we want is we rolled the last dice. What we need is the last dice. We need 7 minus S as the sum, as the last dice. Well, we know that this S goes from, it's at least 2. Like S is greater than 2. So that's fine. Because 7 minus, and S must be here. We need to make S to be less than or equal to 6. And no matter what S is, where S is from 2 to 6, there's always a 1/6 probability of getting a 7 total. Okay. So let's consider the third alternative as to keep 1 dice. Let's say that dice range from 1 to 6. This dice range from 1 to 6. So keep 1, 2, 3, 4, 5, 6. Then what do we need for the other 2? So we need the other 2 with the sum of 6, 5, 4, 3, 2, 1. And what's the probability of each of these? Well, the probability of rolling 2, we cannot get um, the sum equals to need sum of two dice. Uh, That the sum of the two dice cannot be one. So probability of getting a one is zero, and probability of getting two for the sum of two dice is 1/36. And 2/36, 3/36, 4/36, 5/36. And we notice that each of these is strictly less than 1/6. And therefore, if we are able to keep two dice, we should always keep two dice. We should never keep one dice instead of two dice, if possible. And also, because if we can roll all three dice and get the probability of 7 to be 5/72, and 5/72 is right between 3/36 and 2/36, that we should never keep 4, 5, or 6. Okay, so therefore, we never keep 4, 5, 6. Essentially, we keep 1, 2, or 3. Okay? We keep 1, 2, 3, and if the sum is 7, we definitely keep all three. But if the sum is not 7, we always keep 1, 2, 3. And if two of the dice sum up to be less than, okay, so if two dice, right, if three dice sum up to 7, then we keep all three. So our strategy will be never keep 4, 5, 6 if sum of three dice is equal to 7, then we keep all three. If sum of two is less than equal, actually else if the sum of the else if the sum of the two dice is less than equal to 6, then we keep two dice and get the probability of 1/6. And if one dice is less than equal to 3, and else if there are no two dice that sum up to less than equal to 6, and the sum one dice is less than 3, then we keep the last dice. Keep that dice. Okay. If all dice are greater equal to 6, or sum is greater equal to yeah, if all of them are greater than 4, then we just roll all three. And so what we want is we want the probability that he chooses to roll exactly two of the dice, which falls into the last category. That one of the dice is less than equal to 3, and no two dice sum up to be less than equal to 6. And so we can list out all the possible outcomes. If the smallest dice is 1, then the other two must be 6 and 6. Because if one dice is less than equal to 5, one of them is less than equal, the other one is less than equal to 5, then we get two dice sum up to be less than equal to 6. So we must have the 166, and this gives us three possible outcomes. Or we can do 2, the smallest is 2, then the second one, the third one must be 5 or 6. What's the probability of that? Well, the probability is we need to assign which one of the dice is 2. So there are three ways for the dice. Oh, the probability of 166 is the number of ways to get which dice is 6. Sorry, which dice is 1. There are three ways. And there's 1/6 probability rolling 1, 1/6 probability rolling 6, and 1/6 probability rolling 6. Or we can get 2 and then 5 or 6. So the probability of rolling, like assigning the 2, the number of ways to assign the 2 is 3 ways. And the probability of rolling a 2 is 1/6. The probability of rolling a 5 or 6 is 2/6, 2/6 each. Okay, so the first one is 3 over 216. The second one is 12 over 216. Or if the smallest dice is 3, then the other two must be at least 4. If one of them is 3, then we just keep 3, 3, for example. So there are three ways to assign the dice that is 3. Probability of rolling a 3 is 1/6. Probability of 4, 5, 6 is 3/6 each. So it's equal to 27 over 216. And therefore, the sum of probabilities is equal to 3 plus 12 plus 27 over 216, which is equal to 42 over 216. And that's equal to 14 over, no, we cancel out 6, 7 over 36. Yeah, 7 over 36. And therefore, the answer is A. Okay, let me pause the recording again.